Welcome to the MCAT Basics Podcast, brought to you by the physicians at Med School Coach. Each week, Sam Smith breaks down high-yield MCAT topics so you can score as high as possible on test day.
Hello and welcome to Prospective Doctors MCAT Basics with your host Sam Smith. The goal of this podcast is to cover the highest yield topics on the MCAT and provide you with some sort of insight into the questions that the MCAT really likes to ask. This podcast covers work and energy. I'll start by talking about work, including topics like the mathematical and conceptual definitions of work, the sign convention of work. I'll talk a little bit about mechanical advantage and also path dependency. Then I'll get into energy. And in the energy section of this podcast, I'll talk about the general definition of energy. I'll compare and contrast energy and work. And I'll talk about the different types of energy. That includes kinetic energy, potential energy, thermal energy, and total mechanical energy. Then I'll talk last about energy transfer, specifically heat transfer, which there are three types of. That is convection, conduction, and radiation. And this material will show up on one of the four MCAT sections. That is the physics chemistry section. This is all physics, so this is like half of one of the sections. And I hope you find this podcast helpful in your studies, and good luck as you prepare for the MCAT. So the first thing I want to talk about here is work. And specifically, I want to talk about the concept of work. So mathematically, work is expressed as force times distance. That's a pretty easy formula to remember, but I think it's important to also understand what it is conceptually. Conceptually speaking, work is just energy transfer. That's it. A force is being applied to some object over some distance in order to increase the energy state of that object. Say, for instance, I am lifting a coffee mug from my desk to my mouth. That requires work because I am applying a force to the mug handle as I lift it from point A, which is the desk, to point B, which is my mouth. But I'm also increasing the potential energy of that mug. And I'll get into what potential energy is later. Just know for now it is directly proportional to the height of that mug compared to the ground, let's say. So as I lift that higher, I'm increasing the energy of the mug by doing work on it. So again, work is a measure of energy transfer. With that said, let me circle back to the mathematical definition of work. As I said, it's a pretty simple formula. It's just force times distance. And I want to highlight here that this is a scalar value. Work itself is a scalar value, meaning that it doesn't have a direction, only a magnitude. In other words, unlike velocity, which has a direction and a magnitude, I'm headed 100 miles an hour due south. Work only has a magnitude. You can't say I'm doing work in the northeast direction, right? It's just a numerical value. Now, this work equation, which again is force times distance, isn't quite just that simple. In some cases, we need to take into account the angle or direction in which the force is being applied to move some object. Say, for example, I'm pushing a big wooden block across the floor, which for some reason happens to be the favorite physics example of some of these, I guess, unimaginative physics professors. Anyway, say I'm pushing this block across the floor. Now, a force that is perpendicular to the floor on this block won't move the block at all. I'd literally just be pushing the block into the floor. On the other hand, a force that is parallel to the floor on the block would move the block really well, right? I'd be pushing the side of the block, and this would be the optimal angle that force could be applied in order to move this big wooden block. In other words, at this angle, all the force that I am applying to this block would be converted into work. So with that being said, force exerted at angles in between perpendicular or 90 degrees to the ground and parallel or 0 degrees to the ground do varying amounts of work. And so when force is applied at some angle called theta, the work equation becomes force times distance times cosine theta. So we have this other term now that describes the angle between the ground and the angle in which the force is exerted. Now let's look at the limits of this equation. So as I said, when a force is applied perfectly parallel to the floor, the angle between the floor and this force is going to be 0. Now what is cosine of 0? That's just 1. So in the case when this force is applied perfectly parallel to the floor, the equation becomes work is equal to force times distance, which is this original, most simplified version of the equation. On the other hand, when a force is applied at a 90-degree angle to the floor or perfectly perpendicular to the floor, cosine of 90 is 0. And so work is just equal to 0, right? Because force times distance times 0 is still 0. And so you're literally doing no work at all when you're applying a force perpendicular to the floor and you're trying to move an object. So most of the problems you'll see regarding work, at least with this equation, are going to be pretty plug and chug, right? You'll be given probably a force, the direction of that force, and then the distance in which an object is moved. With that said, one thing that is good to know and that you should know is the unit circle, right? Because if the MCAT says that a force is being applied to an object at a 60-degree angle and it's pushed, 10 meters, you're going to need to know what cosine of 60 degrees is, which, by the way, is just 1/2. All right, the next thing I want to talk about here are the units of work. So the general formula for work is obviously force times distance. Now, force has specific units and distance has specific units. Distance is the easiest. That's just some length measurement. Could be feet, could be meters. Force, on the other hand, is typically given in newtons or force pounds. So together that will either be newtons times meters, newton meters, or feet times pounds, foot pounds. And interestingly enough, a newton meter is actually a joule, which a joule is just the units for energy in the SI system. So the units of work are the same as the units of energy, which goes back to the fact that work is just a measure of energy transfer. The next thing I want to talk about here is the sign convention for work. So work can either be positive or work can be negative. And it's important to understand when work is positive and when work is negative and why. And to me, this is a little bit tricky because it seems like work should always be positive, but that's just not the case. Let's go back to the first example that I talked about, which is bringing a coffee mug from a desk up to your mouth to be able to drink. So imagine that you're sitting at your desk right now and you have a cup of coffee sitting on your desk. Now, if you pick up the mug and slowly bring it to your face, positive work is being done. But if you take the mug from your face and slowly lower it back down towards the table, negative work is being done. Now, let me explain why that is. So when you take the mug from your desk and bring it up to your mouth, you're applying an upwards net force and you're displacing the cup or the mug upwards. In other words, force and displacement of the mug are in the same direction. And this is positive work. On the other hand, when you have the mug at your mouth and you're slowly lowering it towards the table, you're still applying an upwards force to that mug, right? Because if you just let the mug go, what would happen? It would just crash to the floor and break. But since you're slowly lowering it, the displacement of the mug is downwards in the opposite direction that the force is applied. In this case, the net force and displacement are in opposite directions. And in that case, negative work is done. Now, this is somewhat confusing. I think the general rule to remember is not that hard. But what I want to do here for a second, and hopefully this helps you understand it, it might be a little more confusing. But if you're finding it confusing, just wait till a little bit later when I just summarize this all. But what I want to do first is I want to compare and contrast the sign convention of mechanical work with the sign convention of thermodynamic work. And maybe that will help you kind of see some of the differences and similarities and maybe help you understand this sign convention a little bit better. Okay, so thermodynamic work describes energy transfer between systems. It's a generalization of mechanical work, which is this displacing an object using a force that I've already been talking about. An example of thermodynamic work would be pressure volume work. This is when gas inside a piston is heated, it expands, and the piston is able to do work based on this expansion of gas. Now, for thermodynamic work, if work is done on the system, its sign is positive, since the system is gaining energy. On the other hand, if work is done by the system, its sign is negative, and this essentially means that the system is losing energy. So let me try to apply that definition to this coffee cup example. In this case, the coffee cup is the system. Now, there are a few ways you can look at this, but to me, the most helpful way to think about it is to look at kinetic energy. So as I lift the mug up, the kinetic energy of the mug is increasing, right? It's speeding up as I lift it up to my mouth. In other words, the mug is gaining energy, or the system is gaining energy. And again, in that case, the sign of the work is positive. Now, when I lower the mug down, it's decelerating as I get closer and closer to the table, and therefore the change in kinetic energy is negative. The mug is slowing down. As a result, you can think about the mug as losing energy during this movement. Hence, the work is negative. The system is losing energy. So with that said, hopefully this was somewhat helpful in helping you understand sign conventions of work. If you're more confused by that little bit, just remember this one rule. If the applied force on an object and its displacement are in the same direction, then the work is positive. If the applied force on the object and its displacement are in opposite directions, that work is negative. Now, one thing I mentioned in the earlier mug example was kinetic energy. And kinetic energy is really tied to work. In fact, there is a theorem called the work kinetic energy theorem that describes this relationship, and that's what I want to talk about next. Kinetic energy is the energy associated with a moving object, and it's equal to 1/2 mv squared, where m is the mass of the moving object and v is the object's velocity. Okay, so how are kinetic energy and work connected, you ask? Well, let me go back to one of my hobbies that I talked about earlier, which is pushing big wooden blocks across the floor. So the block is initially sitting in my kitchen and it's at a standstill. But as I start to push it towards my living room, it will begin to move, and it will move with some velocity. And so we can think about the work that I'm doing pushing this block as altering the velocity and thus changing the kinetic energy of the block. So mathematically and conceptually, work done on an object by a net force is equal to the change in the object's kinetic energy. In other words, if I'm pushing a block of wood from my kitchen to my living room, the work done on that block would be the final kinetic energy minus the initial kinetic energy, or the kinetic energy of the block in the living room as it's moving, minus the kinetic energy it had in the kitchen when it was at a standstill, which, by the way, is 0. Now, other than work causes an object to move, what does this equation or what does this theorem tell us? Why should you give a shit? Well, most importantly, it says that if an object is moving at a constant velocity, then no work is done to the object, right? If the kinetic energy at the final point is equal to the kinetic energy at the initial point, i.e., they have the same velocities, then work is going to be equal to 0. Let me give you a real-life example just to illustrate this principle. Say I'm on a skating rink when I see a Zamboni coming right for me. If you're not familiar with a Zamboni, I'm honestly not sure what it does. I think it lays down ice on the skating rink. Anyways, it looks like this big car or tractor that rides around the ice. And what I want to try to do to the Zamboni as it comes towards me is I want to try to slow it down. And so in order to slow it down, I'm going to try to kind of brace against it as it runs into me. However, when I do this, it doesn't slow down one bit. Instead, I'm being pushed by the Zamboni now, and I didn't do anything to slow it down. So in this case, I exerted a force on the Zamboni, right? I pushed as hard as I could against it. However, its speed never changed. So the work kinetic energy theorem would say that I did no work on the Zamboni since I didn't slow it down at all. So that's one thing that the work kinetic energy theorem tells us. Another is that it tells us that the heavier an object is, the more work that needs to be done in order to get it moving to some velocity. So for example, say I have two wooden boxes. One is 1 kilogram, the other is 10 kilograms. And I want to get each of these moving 10 meters per second. It would take me 10 times the amount of work to get the heavier box moving to the same velocity as the smaller box. So that's kind of interesting. The heavier an object, the more work that needs to be done to get that object up to a certain speed. So overall, the work kinetic energy theorem says that the net work done on an object is equal to the change in that object's kinetic energy. The next thing I want to talk about here is path dependent versus path independent work. And if you're like, what the hell does that even mean? Let me start with this. Path dependent variables are variables in which the path between 2 points that an object takes matters for that variable. Now take, for example, friction. So friction exerts a normal force when I push a wooden block around my house, again, in my free time for fun. Friction essentially converts kinetic energy to thermal energy, which we are basically losing. Now, if I push the block from my kitchen to my living room in a straight line, I'll lose less energy than if I did several loops around the kitchen and then zigzag to the living room. And that's just because the whole time I'm pushing this block, no matter the direction I'm going, friction is exerting a force and I'm losing energy because of it. In other words, the path I take between 2 points matters for friction. For path independent variables, on the other hand, the path an object takes between 2 points doesn't matter. Take, for example, gravitational potential energy. So say I'm driving from Colorado Springs to the top of a local 14er called Pikes Peak. It doesn't matter if I drive from Colorado Springs directly to the top of the peak or from Colorado Springs out to California, then up to the top of the peak. Either way, the change in gravitational potential energy is the same. It's just proportional to my change in elevation from Colorado Springs to Pikes Peak. In other words, the path I take from Colorado Springs to the top of the peak doesn't matter. And again, that's only for gravitational potential energy because it is a path-independent variable. In this example, if we talk about friction, which again is path-dependent, the answer would be different. All right, with that said, let me get back to work. So is work a path-independent or path-dependent variable? And the answer is that it is both. It depends on what type of force is being applied to an object to move it. For a non-conservative force, which is a force that essentially leaks energy, like friction, energy is lost as you push the wooden block around. Remember, friction is a normal force that opposes the movement of an object. And so work that is done by a non-conservative force is path-dependent. However, for conservative forces that don't leak energy, like gravity, result in work that is path-independent. So again, work can either be path-dependent or path-independent, and it all depends on the force that is applied to do the work. The next thing that I want to talk about here is mechanical advantage. So mechanical advantage is a measure of force amplification achieved by a mechanical tool or device. These are things like pulleys, wedges, inclined planes, wheels, axles, etc. And mechanical advantage is just a dimensionless number that is equal to force out divided by force in. In other words, if mechanical advantage is equal to 2, that means I am getting twice the force out of a machine that I'm putting in, which to me sounds a little bit like magic. But it's not magic. Typically how these machines work is that there is less force being applied over a greater distance. And that brings me to my next point that for a machine or a tool, the work in has to equal the work out. And as we know, work is equal to force times distance. So that means that for a machine, the force times distance into the machine must be equal to the force times distance out of the machine. And that means that a machine can work in one of two ways. By increasing the distance over which a force is applied, it can actually decrease the amount of force that's needed to do some task. Or by decreasing the distance in which a force is exerted, the force needed to complete some task can be increased. Think about it this way. The work that's going into some machine is constant, right? This is your finger or your hand pressing down on a lever or pulling a rope on a machine. So that means that the force times distance out of the machine is equal to some constant. So that means that when I increase the distance the force is exerted, I have to decrease the amount of force that's needed. Or if I decrease the distance, I have to increase the force, right? Because that's got to be equal to some constant. So overall mechanical advantage is a measure of force amplification achieved by using a mechanical device or tool. And I think the important thing to remember here is that it's a number that is dimensionless, i.e. it doesn't have units, and it's equal to the force out of the machine divided by the force into the machine. The force into the machine is essentially what force you're bringing to the machine, and the force out is the force you're getting out of that machine. And keep in mind that this number can be less than 1, and if it is less than 1, that means that you're putting in more force into the machine than you're getting out. Obviously, this is kind of a shitty machine, but physically speaking, it is possible that the mechanical advantage is less than 1. The next thing I want to talk about here is the efficiency of a machine. The efficiency of a machine is the ratio between the work the machine supplies and the work that is put into it. And you might be like, whoa. I thought you said that work in equals work out for a machine or a tool. And I'll say that that's only in an ideal situation, right? But we don't live in ideal situations. So when I talk about efficiency, I'm talking more about like real world machines or real world problems here. So the mathematical equation for efficiency is output work divided by input work. In ideal situations, as I said, efficiency is going to be 1 or 100%. But in real life, efficiency is less than 100%. In other words, the work out is going to be less than the work in, unless we're talking about an ideal machine. Now, I want to tie all this together with a real-world example. So let's take throwing a baseball. And by the way, shout out LA Dodgers, who just won the World Series. It's definitely a good year to be an LA sports fan. But anyway, so you're throwing a baseball. When you throw a baseball, your arm is acting as a lever. In fact, there are multiple levers in the arm, right? There's the shoulder, the elbow, the wrist, the fingers. All of these can rotate and act as a lever arm. What allows pitchers to throw the ball, in excess of 100 miles an hour is the fact that the arm can act as a lever. So the force that's exerted on a baseball when you're throwing it is a lot more than the force that's actually exerted by the shoulder. And that is mechanical advantage. Now, just to illustrate this point, imagine somebody pitching a baseball with T-Rex sized arms, meaning like arms that are 10 times smaller than a normal human arm. It's really hard to imagine the baseball going 100 miles an hour after they throw it. And that's because the lever arm would be a lot smaller, and therefore the mechanical advantage in throwing a baseball would be a lot smaller. And it's almost kind of intuitive to see that that's the case. The last thing I want to mention in the work section of this podcast is how it's related to power. So power is defined as the rate in which work is performed. And so mathematically speaking, it is equal to work over time, and therefore has the units joules per time or joules per second. Joules per second, by the way, is a watt. And there are a few different versions of this equation that are derived from that original definition I gave you. The first being that power is equal to force times distance over time, and the second being that power is equal to force times velocity. So those are two other forms to remember for the MCAT. And just keep in mind that a bunch of the physics that's on the MCAT is really just being able to recall which equations to use and recall, what variables you need to pick out of a passage and plug into that equation to get the correct answer. And again, that just goes back to being able to recall the equation and knowing how to work with it.
At Med School Coach, we know that matching into the specialty of your choice and the residency program of your dreams has a dramatic impact on your career as a physician. And your USMLE score is the most important acceptance factor of all. That's why more students than ever are turning to Med School Coach for USMLE tutoring. Our tutors are all 260 plus scorers and have been through rigorous training. Plus, the average student who uses Med School Coach tutoring raises their score by 23 to 55 points. There is an enormous amount of material material you need to know for Step 1 and Step 2, and Med School Coach can help you be smart about how to study. We'll create a custom program just for you. Then, we'll help you master USMLE concepts where you need help most. You'll raise your USMLE score. We guarantee it. Visit us online at medschoolcoach.com and use offer code PODCAST10 to save 10% up to $400 on a Med School Coach USMLE tutoring package. You can achieve your medical school dreams, and Med School Coach can help.
The next thing I want to talk about here is energy. And the first question I want to answer is, what exactly is energy? As I've talked about a little bit, energy is very tied to work, and it's defined as the ability to do work, which is the ability to exert a force causing the displacement of an object. And to me, that definition is a little bit abstract. So what I want to do is compare and contrast work and energy, and hopefully that will give you a better understanding of what exactly energy is. So work is the transfer of energy with the help of a force exerted over a particular distance. Energy, on the other hand, is the capacity to do work. So basically, work is a specific form of energy transfer due to large-scale motions along the direction of an applied force. Let me give a little bit of an analogy. So energy is like money, right? Money can be converted into many different things: food, clothing, housing, and different items that you want. Work is like using money to buy physical items, right? It's a narrower example of energy transfer. In particular, work deals with energy transfer in the form of moving physical objects. Now, in terms of units, energy has the same units as work. That's the joule, which is equal to a Newton times a meter. Not quite as exciting as the joule you are used to. The next thing I want to talk about here is the different types of energy. There's many different types of energy. This includes kinetic energy, potential energy, thermal energy, electromagnetic, kinetic energy, gravitational potential energy, electromagnetic potential energy, and many more. And I'm going to talk about 4 in particular. That is kinetic energy, potential energy, total mechanical energy, and thermal energy. So kinetic energy is the energy in moving objects. And I have already kind of discussed the formula for it a little bit, but kinetic energy is equal to 1/2 times the mass of an object times its velocity squared. In other words, the faster an object moves, or the heavier it is, the more kinetic energy it has. Potential energy is a measure of energy in terms of physical position, and it is equal to the mass of an object times the gravitational constant times the height of that object relative to some starting point, like the ground. The classic example here is a rock that is at the top of a hill, shout out Sisyphus, and this rock has a lot of potential energy when it's on top of the hill, right? It's pretty high up in the air, but once that rock rolls down the hill, its potential energy is converted to kinetic energy as it speeds up, and then once it reaches the bottom of the hill, it's got no more potential energy, I guess, if our reference point is that height at the bottom of the hill. Total mechanical energy refers to the kinetic energy and potential energy that exist for an object or for a system. So total mechanical energy is equal to U plus K, as you'll typically see it represented, or in other words, it's equal to potential energy plus kinetic energy. And I like to think about this as like all the mechanical energy that an object holds. So think about all the energy that goes into getting a skydiver 10,000 feet up in a plane that's going like 500 miles an hour, right? The plane not only has to speed up to 500 miles an hour, it also has to climb to 10,000 feet. And this happens simultaneously in most cases, unless, of course, you fly directly upward. But just think about all the energy that is in this person, mechanically speaking. You have them going 500 miles an hour, that's kinetic energy, and they're 10,000 feet up in the sky, that's potential energy. That's a whole lot of mechanical energy. And of course, the plane requires a lot of energy to be able to actually get this person up that high and going that fast. Now, the last form of energy I want to talk about is called thermal energy. And this is the energy of molecular motion. And technically, this is a type of kinetic energy. Just keep that in mind, right? Because it has to do with motion. But we're talking more on the molecular scale for thermal energy. An example of thermal energy is bringing a pot of water to a boil. The water molecules move faster and faster and faster as they're heated by the stove, and eventually these water molecules can no longer stay in the liquid phase. They enter the gas phase and boiling begins. And this actually brings me to the last thing I want to talk about in this podcast, which are the 3 different types of heat transfer, or the way that thermal energy is transferred to different objects. Now, there are 3 different modes of heat transfer: conduction, convection, and radiation. Conduction is heat transfer through direct physical contact. Take the boiling water example that I talked about earlier, and also say that I have one of those glass stovetops. The pan is in direct contact with the glass stovetop, which gets hot when I turn the burner on, and this heat is transferred from the stovetop to the pan via conduction, via direct physical contact. Also, when you stick your tongue against a cold pole in the winter and your tongue gets really cold and it sticks to the pole, that is conduction. Now, convection, on the other hand, is heat transfer by the movement of fluid. This one is a little bit more abstract and hard to understand, in my opinion. So let me start with the principle through which this works. When fluid is heated, it becomes less dense than fluid that is at a lower temperature and tends to rise due to this difference in density. This is why hot air rises. It's how hot air balloons work. And this is also the principle by which convection works. Take the following example. So imagine you just worked out really hard, and it's also winter, and it's a morning because you went to the gym early, you're really dedicated, good for you. Now, imagine you step outside of the gym and into this cold morning air. What's going to happen is that your body heat will transfer heat to the cold air that's near the skin, warming it. And this will make the air near your skin warmer, causing this warmer air to rise. And then what happens is that this warm air is replaced with cold air, and then the same thing happens. And what happens is that you form this really small, almost microcurrent of air near the surface of your skin, where heat is being transferred to the air and cold air is getting warm and rising, and then is being replaced by cold air. And this process just repeats, creating, again, these little microcurrents. So again, convection is heat transfer via the movement of fluid. Last but not least, radiation is heat transfer via electromagnetic radiation. So we all radiate electromagnetic energy, you, me, and even Dupree. However, humans only barely radiate this electromagnetic energy that I'm talking about. A better example is the sun. You know that if you lay out in the sun for a while, you'll start to get much warmer. And that's because the sun is giving off a bunch of electromagnetic radiation. And it's mostly in the form of infrared, visible, and ultraviolet light. To tie this to another physics concept, which is electromagnetic radiation, we know that the energy of electromagnetic radiation is equal to Planck's constant times frequency. The higher the frequency of light, the more energy that light wave or photon has. So when light waves from the sun hit your skin, the body absorbs that energy, and therefore your body temperature, or at least your skin temperature, rises. And that is heat transfer via radiation.
At Med School Coach, we know that studying for the MCAT exam can be challenging, especially for busy students on the go. That's why our team created MCAT Prep, the only all-encompassing study app built specifically for the MCAT. MCAT Prep by Med School Coach provides student access to extremely high-quality content and a personalized curriculum for free. The app has more than 250 videos, 1,000 flashcards, and 1,000 unique MCAT questions. Plus, MCAT Prep by Med School Coach allows students to create a personalized study schedule and track progress over time. You need every competitive advantage you can get to get into medical school, and now you can put the experts from Med School Coach into your pocket. It's the closest pre-med students can come to a personal tutor without spending a penny. Download MCAT Prep by Med School Coach for free at medschoolcoach.com/MCAT. Or download it directly from the Apple Store or Google Play Store. You can achieve your medical school dreams, and MCAT Prep by Med School Coach can help.
So that's it for this podcast on work and energy. I hope you found it useful in your studies. As always, if you like what we do, please leave us a review on iTunes. It helps in the rankings, and it helps us reach more students. I also want to say that I am working on putting together a full-length audio course for the MCAT. It's going to have some of the same content as my podcast does, but it's going to be a little bit more in detail. The clips are going to be shorter, and there's going to be some room for customization on your part. It's going to be in the form of an iPhone app as well. So be on the lookout for that. I think that should come out sometime in 2021. I'm pretty excited about it, and I think it'll be a great resource for the MCAT.
Each episode of MCAT Basics is brought to you by Med School Coach. To access Med School Coach services, including MCAT tutoring and medical school admissions advising, visit our website at medschoolcoach.com. Good luck as you prepare for the MCAT, and we hope you tune in again next time.